Hello everyone, I'm Zihao, comes from Sun Yat-sen University in China. Today the paper I'm going to present is T-Rank, a lightweight spectrum-based for localization approach for microservice system. First, what is microservice? Microservice is a system architecture that decomposes the whole system into many individual services according to their function, which provides better scalability, faster development, and richer language ecology. But in the loose couple architecture, the system components communicating with each other by network and running individually weaken the system reliability. Because the network traffic is hard to control and the service will be perhaps will be down for the poor resource schedule or some fault of the host they are running. The performance of the microservice system becomes more unpredictable. To discover the system faults and decrease the loss they make, a fast and precise method for localizing the root cause of the fault is essential. However, to deal with this issue, there are some challenges. First, complex service dependence. In the microservice-based system, the services are decomposed into fine-grained components that communicate by the networks. For load balance and availability, most of the services run multiple instances at the same time. The calls between these instances construct a complex service dependencies graph. Second, dynamic system architecture. The characteristic of the microservice is that its updates are frequent, and the logical dependencies between services also change with updates. New service will be added and outdated service will be abandoned, resulting in a more dynamic architecture. How to adapt to the frequent updates and deployments will be an important breakthrough. Third, various and large volume monitor metric. To diverse service, there is a diverse set of metrics such as configuration metric, resource metric, and so on. But some metrics are helpless when analyzing the root cause. It needs a great deal of preliminary domain knowledge for operator to distinguish the relevant metric from so many kinds of metrics. But obviously, it's unpractical. To address the challenge above, we propose a lightweight and fast dynamic system, named T-Rank, to localize root cause in microservice system. T-Rank works based on the special base for localization algorithm, which we call SBFL algorithm, and only relies on the most common metric, the elapsed time, which overcomes the challenge of various metric and dependency graph building. And the core of the T-RAN, the SBFL algorithm, is a statistical algorithm that doesn't need any prior training and the causal graph of the system. The SBFL algorithm finds out the root cause by analyzing the difference between normal traces and abnormal ones and the similarity of the abnormal traces. Let us look at the overview of T-rank. T-rank consists of four parts. A tracing collection, a data preprocessor, an anomaly detector, and the special ranker. First, tracing collection collects the tracing data from the container and store them in the tracing database when a service instance calls another one. And then data preprocessor integrates the tracing data into a tracing chain. After tracing data integration, the data preprocessor classifies the tracing chain by their container dictionary, and then anomaly detectors labels the abnormal tracing chain. And finally, the spectral ranker will calculate the suspicious score of every container by SBFL algorithm to localize the four containers. T-rank provides the ranked suspicious score list of containers to support the system operator to eliminate faults as soon as possible. Let us introduce the four parts in detail. First, the tracing collection. End-to-end tracing is a widely used method, but reviewing the trace data system By reviewing the trace data, system operator can understand how the system running and which component drives in the program execution. In T-Rank, we trace the call between service by deploy a sidecar container for every service instance, which is responsible to generate tracing data when an request is launched and done, and store the data in the tracing database for further analysis. Here are some examples of tracing data. The start time means uh, when the spam start, and the last time means the latency for completing the request. And the attribute is the same, means that whether the request is done or is done successfully. And CMDB ID is the container ID. And the next part is data preprocessor. The sidecar container only records the requests concerned with themselves. Therefore, the tracing data are stored in distributed database and separated. But special ranker needs the whole process of completing the service request to analyze, which means a completed tracing tree. To reconstruct the tracing tree of a service request, T-Rank continuously draw the tracing data from database whose timestamp is in the current time window W, and then integrates them by their trace ID. The trace the tracing data derived from the state service request have have the state trace IDs. So we can integrate the tracing data by their trace ID. After the reconstruction, T1 extracts the tracing trace container dictionary from the containers in it. The key is the name of the containers, and the value is the number of their occurrence. After the integration, data preprocessor classifies the tracing tree into different groups by their container dictionary. The division is strict. The tracing tree is in one group have the same container dictionary. And then the third part is anomaly detector. The goal of the strict classification in data preprocessor is for anomaly detection. Generally, it is unpractical to label every pieces of tracing data precisely. Therefore, the attribute is success in the raw tracing data is not reliable. It's always true, although there is a fault happening. Sometimes some faults in container like network latency will not change its success from true to false because the request is finished at last, but spent intolerantly long time. Therefore, considering such a situation, we analyze the latency for completing the request and find that the latency of some tracing chain increased rapidly when faults happen. We find it's practical to find the abnormal tracing tree in this way. The figure below shows that a loss of outlier in a tracing train group can be labeled by it. To find out the abnormal trace, based on the strict classification, T-RAM proposes a simple and rough anomaly detector, which makes use of the metric the elapsed time. T-RAM assumes that the elapsed time of tracing tree in a group uh, conforms to the normal distribution. In the normal distribution, the possibility that the absolute value of the mean minus true data is out of 3 times the standard deviation is 0.0026. Hence, the tracing tree whose elapsed time is out of this range can be considered as abnormal. Combined with the attribute is that anomaly detector can label most of the abnormal tracing chain. Here are the uh, formulas of anomaly detector. And the core of the T-rank is the special ranker. As we just said, the SBFL algorithm finds out the root cause by analyzing the difference between normal traces and abnormal ones and the similarity of the abnormal traces. The full localization component of T-rank special ranker is adapted from the SBFL algorithm. Special ranker statistics the coverage information of containers in the survey request and calculates the container suspicious score using a risk evaluation formula. So for the special ranker, uh, the fail case is necessary, and it will get nothing if all test cases are successful. Therefore, the anomaly detector is significant. Special ranker treats every tracing chain as a test case T and every container C as an element in the test case. The definition of notation about C in special ranker is shown as follows. EF is the number of failed tracing chain TF, which includes the container C. EP is the number of successful tracing chain TS, which includes the container C. NF is the number of the failed tracing chain TF, which doesn't include the container C. NP is the number of the successful tracing chain TS, which doesn't include the container C. There are many kind of as for the risk evaluation formula, there are many kinds. Here is one of them, the OCI formula, which makes the best performance in our experiments. According to the definition of notation, we can describe the process of special ranker like this. First, the anomaly detector will polarize the group set of tracing chain, and the special ranker will extract the container set C from the group G. And for every container C in the container set, special ranker will statistic the four parameters of C in the group, and then calculate their suspicious score by the risk evaluation formula. And then after calculate all container suspicious score, special ranker will sort the list by their suspicious score and provide a ranked suspicious score list of so let us take an example to understand how the T-rank works. Take this model as an example. IQ1 and IQ2 correspond to tracing chain group G1 and G2 respectively. We inject force in Docker 01. So many tracing chain includes Docker 01 failed, and the trace data clarity and preprocessed is like the table below. After using the risk formula OCI, it is obviously that the Docker 01 have the highest suspicious score, and the operator should check it to find its bug. Now let us introduce our experiment. We use the data provided by a Chinese company, China Mobile, to test the effectiveness of T-rank. In the first experiment, we tried to use 25 different risk formulas to inspect whether they made any difference in T-rank performance. And the results show that the formula focusing on the parameter EF have better performance. And then we explore whether the volume of data for analyzing affects the T-rank performance. So we experiment with different data collection window size W, which affects the data volume. The experiment result shows that when the window size is 4 to 5 minutes, almost 1 million pieces of data of trace, T-rank achieves best performance. To find out the reason why the best window size is 5 minutes, we pick up the few force injection period data to analyze the exam score change of different window size. When the right figure show the result. When the fault just happened, the useful tracing data for localizing the fault is limited. So no matter what the window size is, their performance is close. But when the faults last for a while, the larger window size can get more useful information by including more historical tracing data. On account of it, they can provide a more accurate suspicious score list. If the window size keeps increasing and even larger than the for lasting time, the data before false happens will be a noise to disturb T-rank's judgment, resulting in a worse performance. At last, we compare T-RAM with other state-of-the-art methods. The comparison result shows that T-RAM outperforms the previous methods, achieving 1% higher precision and 8% higher records than the best performance method MS rank. T-RAM makes a great improvement, but the performance of T-RAM is not as good enough as we expect. After analyzing the detail in the experiment, we found the improvement of the precision is smaller than the improvement of record is because is is for the reason that T-RAM generates the suspicious score only when the anomaly is detected. But the anomaly detector of T-RAM is too sensitive because its purpose is labeling as much as possible abnormal tracing chains for localization. This characteristic may more false alarms. But if there is a fault container, T1 can localize it precisely. Combined with other anomaly detection tools, T1 can achieve better performance. We will make further research in this way. And T-rank is a lightweight method. We statistic the time and resource consumed by T-rank. When T-rank is running, processing the tracing data within 5 minutes only takes 6 seconds, at most with one CPU core, which is much less than the window size, and only a little CPU resource is consumed. This paper proposed a performance dinosaur system named T-rank for microservice-based systems. To address the root cause localization problem, the purpose of T-rank is to offer a rank suspicious score of the containers based on the spectral SBFL algorithm. T-rank has higher accuracy, low resource cost, and low time consuming, which is quite practical. Moreover, as the scale of a microservice system become larger, T-rank can also help operator localize the root cause due to its lightweight property. That's all my presentation. Thank you.